In this particular video, we have water that flows from the left side of the pipe to the right side of the pipe. This pipe here has three different segments. R1 here is known as 2R, R being capital R here in the middle section. And then on the right side where the water exit, the radius here is given as 3 capital R. So it's kind of normal, narrow, and then wider. Okay. It says the speed in the middle section is 0.5 meters per second. And it says what is the net work done on zero point 0.4 meters cube of water. So 0 0.4 meters cube here suggests volume. Meters cube is a measurement of volume. And then it says from the left section to the right section. The density of water here is a constant. It is 997 kilograms per meters cube. I want to use this because the volume given in this particular problem is 0 0.4 meters cube. So I want to make sure all my units are the same, okay? Because sometimes you can see the density of water in grams per centimeters cube. But here, I'm going to use kilograms per meters cube because the volume here is given in meters cube. All right, now let's go and crack it out. The first statement you should start with for this problem is net work is equal to change in kinetic energy theorem. And then to find delta Ke, you can break that up into Kf minus Kei. Well, you can further break Kf into 1/2 mvf squared minus 1/2 mvi squared. And at this point, if you want to, you can, you don't have to. I'm just going to go ahead and factor out the 1/2 and the m. Both these terms have a 1/2 and an m, so I'm just going to pull that outside. So really, it just be vf squared minus vi squared in parentheses here. You don't have to, but if you want, you can, because then you would just have to plug the value of m in your calculator just once rather than twice, okay? That's up to you. So the first thing I wanted to find is the mass. Here, in order to find net work, I need m, I need vf, I need vi. The particular problem already gave me volume, which is 0 0.4 meters cubed. The density of water is a constant, so the only thing I really don't know is the mass of the volume that's being pushed here. So to find m, I'm just going to multiply both sides by the volume of the water that's given, and that is 0 0.4 meters cubed. Density here, based on what I'm using, is 997 kilogram per meters cubed, so I'm just going to go ahead and plug and chuck here. So density, I'm going to substitute it out for 997 kilograms per meters cubed. Volume is 0 0.4 meters cubed. Meters cubed on the bottom left, meters cubed on the top right cancels out. So the only unit left over here for mass is 398.8 kilograms. Okay. Now that I know m, I still need to figure out what vf is. I still need to figure out what vi is. But that's not bad. Okay. The continuity equation tells us that the speed of the water as it travels through the pipe speeds up or slows down based on the cross section. So here R1 is 2R. And then it goes through the middle section, which is more constricted, is more narrow, so therefore it has to speed up, right? The same mass has to get pushed through these pipes in this given same amount of time. So here, the green arrow in the middle section, I'm just going to draw it longer so it's faster. And then as it exits, though, in this particular region to the right, where the cross section here is 3R, it's going to slow down. Okay, so as it gets wider, it slows down. So I'm just going to draw this V really, really small. So as you can see, throughout the whole entire time, as water flows through this pipe that's given in the diagram, it's whatever speed it enters, it speeds up, and then it slows down. Okay, we need to figure out what the V on the left is and what the V on the far right is, because this is the initial speed, and then this is the final speed. So to do that, we can just use the continuity equation. So here, we can say that A1V1 is equal to A2V2, A being the cross-section area, and then V being the speed. So I know what V2 is, so I'm just going to go from left to middle. Okay, so please keep up here. I want to say this is 1. The middle section would be 2. Okay, so I need to figure out what V1 is. So to get V1 by itself, I'm just going to divide both sides by A1. Now I can just go ahead and plug and chuck really, right? The radius for the left side of the pipe is given in the wording. It says R1 is equal to 2 capital R, so I'm just going to go ahead and label that as 2 capital R. So to find area, A1 and A2 here in this function, well, area is just simply pi R squared. So make sure you're careful with what R you plug in though. This is A2. That puts me right in the middle part of the pipe here. And the middle part of the pipe, the radius is just known as R. So in the numerator, it's just pi r squared, because the function for area is just pi r squared. But make sure you pay attention to what r you plug in. Well, V2 here is 0.5 because I want to go from left to middle, left being the first, middle being the second. So the speed of the middle section here of the pipe is given as 0.5 meters per second. Okay. On the bottom, area once again is is pi r squared. So here's pi. However, it's important to have good habits. Um, the left portion of the pipe here, the radius is 2r. So make sure you use parentheses because if you don't, you're going to goof here, okay? So r is really 2r. So I highlighted here. So you notice I wrote my 2r in parentheses. Why? Because that's going to trigger that I need to distribute this exponent, okay, into the 2 and the r squared. Again, generically, area is pi r squared, but r for the left segment is actually 2 capital R. So use parentheses. So therefore, if you distribute the exponent, you'll get 4 r squared. Okay. So on the numerator, as you can see, you have a pi. That's going to cancel out on the bottom. And then if you square things properly, there's an r squared on the top, and therefore there's also an r squared on the bottom. So that's going to cancel out. So the only thing that's left in the numerator is just 0.5. The only thing that's left in the bottom denominator here is just 4 because 2 squared is 4. So if you simplify this on your calculator, you get 0.125 meters per second. And I want to use the same strategy to find the exit speed on the right side of the pipe. Okay, so I want to say that continuity-wise, it suggests that the flow rate in the middle section must equal to the flow rate to the right of the to the right side of the pipe here. So I can say A2V2 is equal to A3V3. So here, I know what V2 is. I need to figure out what V3 is because V3 is my final velocity. So once again, just in case you're not keeping up, Vf here is V3, Vi is V1, right? Because you need to know how much work is done as the water flows from left to right side of the pipe. Okay, so here I need to solve for V3. So to solve for V3, I'm just going to divide both sides by A3, and I can just use the same strategy really. R3 here in the wording is given as 3 capital R, so I'm just going to label that. Okay, so make sure you label your R's carefully. A2 in the numerator, and my function hasn't changed. A still, by definition, is pi r squared. What R? The middle segment, R is just capital R. So I'm just going to go ahead and plug in R, and that's R squared because it's area. Pi r squared is the area. Well, what's V2? V2 is 0.5. Now, on the bottom, though, once again, you got to be careful. For A3 is pi r squared generically. But what is the radius at the right segment? The radius is given as 3 capital R. So I'm going to go ahead and plug in 3 capital R in parentheses. And then that's going to get squared because the function generically is pi r squared. But in this case, the radius is 3 capital R. Okay. So likewise, over here in the middle section, pi cancels out. And if you square the denominator, you get 9r squared. R squared is going to cancel out. So the only thing left in the numerator is 0.5 again. The only thing left in the denominator is 9. And then 0.5 divided by 9, you're going to get 0.055555 running. So I just round up to 0.0556. So now that we have V1 and V3, or VF and VI, we just go ahead and plug that in. So once again, I factored out M earlier. Like I said, I just want to plug mass in once. So the mass I calculated already using using density is 398.8 kilograms. VF on the right side of the pipe is slow, so that's 0.0556, and I want to square that, and then minus the entry speed of the water at the left side of the pipe, which is 0.125, and don't forget to square these terms. And other than that, if you plug in your calculator correctly, you should get a value of about negative 2.5 joules. Okay, all right, I hope that helps. Stay nerdy, don't be bye.